Yeah, g'day, it's Charlie ZL2CTM. Well, I just wanted to do a quick video today just to, I guess, wrap up where I've got to with the variable frequency oscillator as part of this little COVID-19 sort of AM radio that I was sort of pottering around with for the 5.9 to 6.2 megahertz shortwave band. You recall that I wanted to use this nice reduction gearbox here with the capacitor for the main tuning capacitor for whatever the VFO was going to be. This particular one here, as you can see, as I go clockwise looking for a high tuned frequency, so to speak, the capacitance is decreasing, and as I go back the other way I've got increasing capacitance there, just monitoring the output there of the general purpose or general coverage receiver there. You can see on the scope up there the output of the oscillator. As we'll see in a sec, there's three stages there. There's the main oscillator, there's a buffer amplifier, and then there's a little Class A amplifier at the back, which will be required there to give me the 1.414 volts peak to peak that I want as a 7 dBm drive for that 50 ohm double balance mixer that I want to use for the first mixer. In terms of what I'm doing there, so we just mentioned that a clockwise rotation was resulting in a reduction in capacitance, which because I want to use high side injection with this little 3.18 megahertz IF, I want to basically have it that as I turn clockwise I want my oscillator frequency to also increase. So that's why I've elected to go with this configuration. So for that 49 meter band, it's 5.9 to 6.2 megahertz. So therefore I want to have a frequency of oscillation out of my VFO here ranging from, at the low end, 9.08 to the upper end for 6.2 megahertz of 9.38 megs. And as we can see there, we're currently sitting there at 9.18, sort of halfway between the two. Where we go? There it is. Yeah. So let me just, what else I want to talk about before I turn it off and we'll have a look inside. So that was basically the configuration I wanted to run for. As we see, the output there is nice and clean. Didn't have to use any filtering, which is good. So like I say, just the three stages that we'll have a look at now. Other than that, from a stability point of view, let me just tune in there, so I hope that's not too loud. The good thing is I can bring my hands all around, I can bring up there, I can tune, and the frequency is not changing, which is nice. I can touch things. The only frequency sensitive one is the hot side of that variable capacitor, which is that red wire there. As you can imagine, if you get close to that, then things go crazy, but the cold side is fine, or the earth side. So in terms of actually being able to operate it, and the reason why this is so thin is because it's going to sit up here in the on the bookshelf between a couple of items. So I've just made it nice and sort of narrow. That's why it's sitting on that sort of narrow piece of wood. Again, that's just the way I like things, and it's just sort of pottering around. So anyway, like I say, from a stability point of view, that's good. There's no hang capacitance going on there, which is nice. Right, well, I'm going to turn that off. Let me just turn that off so we don't blow anything up, and we'll have a look inside. And then I'll go through the circuit and where I got to with that. So, as you can see there, I didn't have, unfortunately, any ready-made metal cans, so I just elected to use some pre-cut single-sided board that I had lying around the shack. So I've got the copper on the outside, which made it a lot easier just to sort of tack weld, so to speak, the box together. And then I had an existing metal cover here which I'm just using. So that became the template for the size, and I just lived with whatever it was. As you can see down inside, hopefully without too much reflection of the lights. Let me come in this way a little bit. So down there we have the three boards. We've got, let me see if I can just zoom up there a little bit. On the top here we have the actual main oscillator itself, and as you'll see that turned out to be a Colpitts. So we can see our split capacitors here, and then down here we have two sets of capacitors which I'll talk about. The main capacitors that sit across the inductor and the main tuning capacitor, and then another smaller value there, which was required in series with the main capacitor here to set the range of frequencies. Again, we'll look at that in a sec on the circuit diagram. The actual inductor itself came out of one of those old radios that I had. In the end, I just elected to not tinker with the turns ratio on that, and just kept it as it was, and then made the capacitance to suit. There is a small slug that sits inside here. At the moment that's pretty well out, and then you can just basically move that in and out just to tweak the inductance, which I thought I'd use as opposed to using a trimmer capacitor sitting across here, an ear core trimmer. The reason why I've tried to go for a number of smaller values to come up with the overall capacitance was to try and shed or share the thermal load, the RF thermal load, across more capacitors to increase the stability. On the top there, coming out of the output of the main oscillator, is the buffer amplifier. That's also a J310. Again, we'll look at the circuit diagram in a sec. Then over the back there, it just drops down into that Class A amplifier down the bottom, which you can just see there, which is a 2N3904 set up as a Class A amplifier. And on the input to that amplifier, it's got a little 10K trim pot there, which we'll see in the circuit diagram, which allows me then to ultimately set the output across that 50 ohm load, which ideally I want it to be 1.414 volts, which reflects that 7 dBm for a 50 ohm for the 50 ohm mixer. So that's the configuration there. In hindsight, I probably could have mounted that inductor sideways and then made the box a little bit shallower, but that's fine. And the other thing I try to do, sort of emulate here, is to have the oscillator and its buffer amplifier sitting sort of raised off the metal floor and sort of sitting away a little bit from the metal casing there, and which is sort of the configuration that I saw in a lot of the commercial radios, that they didn't have the oscillators sitting on any kind of earth floor. They were sort of quite elevated and only held in the four corners of the circuit boards, which were then earthed. Other than that, the rest of the circuit board itself was sitting not well away, but certainly away and not directly adjacent to earthed surfaces. So that's the reason why I try to emulate that. So I've got nice big thick wire there that doesn't move, just to reduce the microphonics and give it a sort of a mechanical stability from that point of view. Yeah, so basically that's the, I guess, the configuration of the VFO box. And like I say, with just a press fit lid there, just to where's that zoom there, to basically finish off the box. Right, so like I say, from a power point of view, which we'll look at, 2 voltages going into it. There's 6 volts, which feeds the main oscillator itself and the buffer amplifier, and then 13.8 volts, the main VCC for the rest of the radio, is feeding the little Class A amplifier, and both decoupled at the point of entry with a 10 nanofarad capacitor, just 2 junk box capacitors that I had. I've got a ton of these, so I elected to use those as opposed to, say, 100 nanofarads. And then down the bottom, just a little stock standard simple LM317 voltage regulator. Nothing special with that circuit. That's straight off the data sheet. That's dropping our 13.8 volts down to our 6 volts for, like I say, the oscillator and the buffer amplifier. Okay, so just pushing that aside, what I did play around with for the earlier parts of experimenting with this was a Hartley oscillator, using the configuration that's, well, it's a stock standard configuration, but this particular one came out of the solid state design for the radio amateur. Elected to use, like I said I was going to in the first place, a J310. That particular Hartley has a 4148 from the gate to ground and 100 kilo ohm gate resistor to earth. This worked well. There was actually nothing wrong with this. Again, I elected to use another inductor out of one of those old radios. This was set up as a fixed inductor of, without those new turns there, this many turns. So what I decided to do is I measured that, the inductance, and I decided, well, what I'll do is I'll aim for 10 microhenries for inductance, overall inductance, noting that I need to have a tap a quarter of turns up. So in the end I just added another sort of 5 or so turns there, inserted a tap which is roughly now a quarter of the way up, and then coated that with a nice decent coating of my my daughter's nail polish, and like I say, that went really well. The reason why I didn't elect to stick with the Hartley is because the this is the main capacitor here, roughly 33 picofarads on that particular capacitor I'm using here, and in order to get that range of capacitance to give me that 9.08 to 9.38 megahertz output range, this particular trimmer capacitor here had to be quite small, and yeah, and in fact this capacitor up here too, that was feeding or taking some of that RF energy into the J310, was also small. And while it worked really well on the bench lying on a piece of wood, as soon as I introduced that into the shielded case, there was so much, I guess, my assumption here is there was so much parallel stray capacitance between the shielded box itself and the various components of the oscillator that it just went out of oscillation. And I potted around all the different various values and elected to say, well, okay, it was a good experiment and it was nice to be able to play around with the Hartley. Let's go and have a play with the Colpitts, which is exactly what I did. So what I've settled on, right or wrong, is a Colpitts oscillator. Let me just zoom out there so we can sort of see what's going on. So as we can see, so C for Colpitts, therefore it's got split capacitors. That's the way I remember it. This is our configuration here. We've got that inductor which we've talked about there that I'm using. We have our main capacitor there, that 33 picofarads capacitor. We've got what I'm just going to notionally call that smaller CM for the main. We've got our CP, our parallel capacitance. That's getting this overall frequency in the right sort of ballpark, and then fine tuning with that slug. We've got our series capacitor there, and like I say, those two split capacitors here. Essentially the same configuration in terms of biasing as the Hartley, so 100 k ohm resistor there and the 4148, and a small value capacitor coming out. What I did when I made this is, and we'll look at the other two circuits as well for the buffer and the main amplifier, is I built them in stages. So I elected to build the oscillator first, and then I used as a load just a 100 k ohm resistor, because I knew that my buffer amplifier was going to have 100 k ohm and a very high impedance of the J310. So looking in here, it's going to be probably driven by 100 k ohm. So that's what I did. I did in stages. So I built the stage first, drove it into 100 k ohm resistor, scoped that, got this working nicely, and then added the other stages. If you look at solid state design for the radio amateur, it sort of gives you sort of some starting points for working out some of these values here. For example, this what I've called the series capacitor here, it talks about having a capacitive reactance of around 100 ohms. And we know that XC equals 1 over 2 pi FC, so therefore we can rearrange that formula to try and work out what that CS needs to be, given roughly 9 megahertz, which is sort of in the middle of the range of the output of the VFO. Solving for that comes out at 176 picofarads, so I elected to use just 150 puff. For XC1 and XC2, so the split capacitors there, it talks about 45 ohms. So again, solving for that, it came out at 392 picofarads. I looked in the box, I was looking for some NPO caps, and I had a couple of 270s. So that was my start value, was two 270 picofarad capacitors. XC0, that's the output capacitor there. Talked about in terms of the SSD array using 750 ohms as a capacitive reactance for that. Again, rearranging and solving comes out at 23 picofarads. Rummaging around in my box, I had a 47 picofarad capacitor NPO. Now I'm pretty sure this one here is not so important when it comes to the driving the overall frequency of the oscillator, but I elected to use an NPO for that one, so that was the closest one I could find. So I started with those values, and with a bit of trial and error, I had too much capacitance here that I couldn't easily trim out. So in the end I dropped both those split capacitors down to 100 picofarads, and then I ended up with my parallel capacitor here turned out to be, I ended up with 3.3 in parallel with 1.8 in parallel with 2.2 was about right, and then that main capacitor here, and again this was all through trial and error just to get, for example, the spread, or the VFO spread or range, whatever you want to call it, correct, was quite a little bit of trial and error. I initially used a variable trim cap here to get it spot on, and then I measured that and then recreated that capacitance using fixed lumped components. But anyway, that value there turned out to be 10 picofarads in parallel with 2.2 and parallel 1.8. So that overall capacitance there on the meter was the same value as I got using the ear core trimmer. And like I say, C1 and C2 turned out to be 100 picofarads. So that was good. So that basically gave me what I wanted. It got the resonant frequency in the right range, and then the spread as I tuned from one end of the main capacitor from minimum capacitance through to maximum capacitance gave me what I was after, of that 9.08 roughly to 9.38. I'm ever so slightly on the low side and ever so slightly on the high side, which is what I wanted. So where I wanted to actually tune from 5.9 to 6.2, I'm tuning from 5.85 up to about 6.23. So I wanted to err on the side of safety. So that was good. Right, so that was the main oscillator itself. Like I say, I settled on a Colpitts using a J310. The RFC there, I didn't mention, just went for 10 turns on an FT37-43 using number 22. So nice and thick, just trying to minimize any variations there in inductance, and just making sure that its own resonant frequency was nice and low. But that's what I've stuck with for all the RFCs in the circuit. So that was the oscillator. So the buffer amplifier, just to give that oscillator a nice sort of constant load to stop anything being pulled with the downstream loads. Again, just stuck with the J310. In this particular configuration here, with a common drain, and just taking the output off the source there. Again, the RFC, exactly the same configuration, 10 turns on an FT37-43 with some heavy number 22 or heavy-ish gauge wire there. You'll note from an earlier video I'd already determined that that large batch of J310s that I had sitting in the junk box had a pinch-off voltage of minus 2.1 volts and a current through it with 0 voltage on the gate, or an IDSS of 32 milliamps. So therefore I could plug them into that formula there to determine what my ideal source resistance needed to be, and plugging those values in down here comes out at 92 ohms, hence the reason why I've gone with that sort of standard nearest standard value of 100 ohms. Again, because I built this in series, so I now had the oscillator sitting on the input, this was sitting on the output. I knew the oscillator was good driving 100k, so I just bolted it straight on, and then had that driving a 100k, say again a 10k trim pot. So it was just a 10k resistor simulating that trim pot that I was going to use for the amplifier, just to make sure that the output was nice and clean and there was nothing untoward going on. And that was working fine. What else to mention here? So again, as I did for the actual main oscillator itself, just a 100 ohm resistor there on that 6 volt supply, just to try and provide a little bit more sort of isolation from any variances there. Noting that's pretty good because it's coming from that LM317, which provides some isolation anyway. Right, what else to mention? So yeah, so that was the buffer amplifier, and then I had that feeding into the main amplifier itself, and the whole aim of this amplifier here is just to boost the output of that buffer amp, like I said before, to get up to that 1.414 volts peak to peak across that 50 ohm load. In other words, 7 dBm for that little mixer, that ADE-1. Nothing special in this little amplifier here, Class A, just elected to have a quiescent DC current through it of 10 milliamps. And funny old thing, the numbers there is what we've seen many times before, because it's a common sort of amplifier that I've been using. Stock simple. I'm not worrying about the reactive components of the input and output of that device here, just purely looking at the resistive side of the house. What else? So I'm not going to go through the maths here. I'll put all this up on the blog for people to look at, but exactly what we've seen before. Just looking at our geometric mean for the beta DC. As I said, 10 milliamps is the quiescent current. Once again, setting the emitter voltage to be 1/10 of VCC, so 1.38 volts there. And right, full stop. So for the that T1 transformer there, just again, I'm not trying to eke as much drive out as this, because I'm only after that 1.414. So I've just gone with transforming that 50 ohms up to a 200 ohm load for the collector. So just going down there. So I know if I want to transform 50 ohms up to 200, then my turns ratio is the root of the impedance ratio. So 200 over 50 square rooted equals 2. And I know for this frequency range here that a 12 turns to 6 turns on an FT37-43 is going to be about right. So just looking at that rule of thumb again, the smallest winding is 6 turns, and I want to make sure that the inductive reactance of that particular winding is that sort of 4 to 5 times the load that's going to be hanging off that, which in this particular case will be 50 ohms. So we know that 6 turns on an FT40, say again, 37-43 is 12.6 microhenries. XL equals 2 pi FL. Therefore, at 7 megahertz, it turns out to be 712 ohms, which is big tick greater than 4 to 5 times 50 ohms. 5 5s are 25, so 250 ohms would be more than that. So that's good. So that's all really. So like I said, it's the amplifier, that's the buffer. I'll put all this up on the blog, so it may be of use. Again, normal caveats, I'm no expert in this. I just potter around and play around and try and make things work and learn as I go along. So let that be the caveat. What else I want to sort of mention on this potentially? Stability wise, not too bad. I need to measure that fully in terms of its warm up, but for what I'm wanted to do, it seems to be really good actually. Quite happy indeed with that. So the process now is to spend today looking at the bandpass filter coming in. I'm going to use LC for that. It's that sort of free software for doing LC inductors and capacitive filters, and then into a probably an RF amplifier into the mixer. Like I say, it's on a pretty thin board there because it needs to fit in that sort of slight small gap up there. But I'll rearrange this, but that should be enough there for, because it's only a receiver, having the down this end the bandpass filter, a little amplifier into our into the mixer, a couple of stages of IF with the filter in the middle, and then up to the side there will be the audio frequency amplifier. So I don't see that being too much of a problem at all. And like I say, this is not supposed to be a commercial fantastic radio. It's just about sort of having some fun and better understanding how these things work in terms of an analog VFO as opposed to some of the digital ones I've been using, and then playing around with the AEM detection, which will be a bit of fun and games. Right, well, I'll say a big 73s there. Stay safe, and we'll keep plodding around, and any questions sing out. But like I say, right or wrong, I'm no expert in this. This is just all about playing and having some fun. Okay, cheers all.